As you probably know by now, but some people will see forgotten, the recordings will be in each week's modules now. I'm recording them on my computer, and therefore I'm posting them in each week's modules. And there's no passcode required for that. So the ones that were done previously on the cloud, they're still there, but the ones that I'm doing now are in Canvas, posted directly into Canvas. Okay, so just know that if you want to review. Now today's schedule, I'm going to do a brief review of what we've covered so far in confidence intervals, and then I'll be going over two new types of confidence intervals in StatKey. That will take me to about just a little bit before 2:40. I'm going to start the quiz a little earlier today. And the quiz I'm going to extend the time a little bit for the quiz. I'm going to make it 30 minutes instead of 20 minutes. So please pay attention to the review, because it will help you with the quiz. Now the quiz, what I've done, I might have mentioned that I was going to walk you through it, but I was able to copy and paste StatKey graphs into the quiz, into Canvas. And I think they're pretty readable. So basically, you won't have to create anything in StatKey yourself. It'll be displayed in each question of the quiz. All right, so it won't be necessary for me to walk you through it. Pretty self-explanatory. Okay, so let's get started. And what I'm going to do first is go to the textbook. Okay, and let's just review what a confidence interval is and the different parts of it. Now, a confidence interval is a way of estimating a population, either a population mean or a population proportion. And it estimates it using sample data. And so the sample data will give us either a sample mean or a sample proportion. And then what we do is we estimate it. Well, let's put it this way, the traditional way of estimating what's called a confidence interval is, number one, we have to create an interval of values around the sample statistic that we come up with for the one sample that we have. And what do? We simply take our sample statistic and add and subtract what's called the margin of error. So this is the way we do it through formulas. And you're only responsible, as far as reading is concerned, for the first two sections here of chapter 20. So they talk about it here in chapter 20 that you, to create a confidence interval, you add and subtract the margin of error. Now, the margin of error, how do you calculate it? Well, that's something that is done later on in this chapter, but you're not responsible for. But just so that you have an idea of how it is calculated, what we do in terms of finding a confidence interval for a proportion is we, first of all, calculate that margin of error. And how do you do that? Let me just see if I could find that page. So we do it by, first of all, calculating what's called the standard error. And again, you don't need to know this, but it is in chapter 19 when they talk about the rule for sample proportions. They talk about the standard error, and it's the square root of the proportion times 1 minus the proportion divided by the sample size. It's the square root of that whole thing. Now, you don't have to calculate that. You just know that you have to be somewhat familiar with it. And then what the book talks about is that you take that standard error and you multiply it by a multiplier. I think that's the way they talk about it here. So there's some multiplier that's associated with what? It's associated with the confidence level. So we'll talk about what confidence level is in a second. So the confidence level determines the multiplier. And then we take that multiplier and multiply it times the standard error. And what do we get? The margin of error. All right, so that's how it's calculated through formulas. Again, you're not responsible for that, but you have to understand the general idea of how to create a confidence interval using formulas, is that you add and subtract a margin of error to the sample statistic, whether it's a mean or proportion. That's what you're doing. All right, that's what you need to know, that particular idea. Now, what is a confidence level? Confidence level, it has to do with how confident are you that the interval that you've created from the one sample that you have come up with, it does contain the true population mean or true population proportion. How confident are you? And how do you determine that confidence? Well, the confidence level says the following. If I created many samples of the same size from the same population, all right, many samples, and I calculated the sample statistic, either a sample mean or sample proportion for each one of those samples, then if I'm going to be 90% confident, then I would estimate that 90% of all those samples would actually contain within the interval the true population mean or true population proportion, and 10% wouldn't. If I was 95% confident, then I'm confident that 95% of the intervals contain the true population mean or the true population proportion, and 5% don't. And if I'm 99% confident, that means I'm estimating that 99% of all those samples have confidence intervals that contain the true population mean and true population proportion, and 1% don't. Now, it's obviously better to have a confidence level that's higher. But the problem with that is when the confidence level increases, the interval becomes wider, which is not a great thing. We don't want wide intervals because then the estimation is not as good, all right? Because there's more variability around the sample mean or sample proportion. So it's not better necessarily that we increase the confidence level because, again, we have wider intervals. If we lower the confidence interval, we have narrower intervals, which is better, but we don't want low confidence levels, lower confidence levels. So what do most people use? They use 95%. It's sort of in the middle, all right, 95%. It's not as high as 99%, but it's higher than 90%. And the interval is wider than the 99% interval, but it's not as wide as the 90% interval. So it's sort of like a compromise. So again, most people use 95%. But occasionally you'll see research where people use 99%, some people use 90%. All right? So that's what a confidence interval level means. It does not mean a probability. All right? I've said that, 1,000 times in the last couple of videos, but I'll say it again. A confidence level does not mean probability. If you get a confidence interval, it does not mean that the probability is, let's say you have a 95% confidence level. It does not mean, I'll say not mean, that the probability is 95% that the true confidence, the true population proportion or mean is inside that interval. No, it does not mean that. It means that you're 95% confident that that interval contains the true population mean and true population interval, based on the idea that if you looked at all possible samples, that this particular interval would hopefully be one of those 95% that do contain the true population mean and true population proportion. All right. So just know the difference between those two ideas. Any questions about any of that? Now, chapter 21, if we go back, let's go to 21. 21 has to do with confidence intervals for means. And there's no big difference between proportions and means in terms of constructing a confidence interval if you're going to use formulas. Once again, you're going to add and subtract a margin of error to the sample mean. That's literally what you're going to do if you're using a formula. Okay, so they just, give examples in here of how it's done. And it's only I think the only thing you're doing is looking at the the construction process. They're telling you what the standard error is here. It's a population standard deviation divided by the square root of sample size. Again, you don't need to know that, because we're not going to construct a confidence interval using that. And then once again, you're going to use a multiplier times that standard error, and that'll be your margin of error. That's the formula way of doing it. All right. All right. And again, once again, you can read through this, but basically it's the same idea with means as it is with proportions. All right. So let's go to, let's actually go to StatKey now. Give me a second and highlight StatKey. Once again, I hope you've been playing around with StatKey a bit. I did go over it in the videos, how to use it. I did sort of warn you that if you don't become familiar with StatKey, and then you have a quiz or a test, and you're learning it for the first time when you're taking the quiz or test, or trying to learn it, it's not a great idea. So I hope you've been playing around with it so you're somewhat familiar with it. Hopefully listening to the videos that I recommended, all that sort of thing. So anyway, this section in here shows you how to create what are called bootstrap confidence intervals. This is the alternative to using formulas, all right? So formulas are what the book says to use, and that in most statistics courses, that's the way you learn how to create confidence intervals. But with this StatKey program, we're using an alternative way of doing it, which is through simulation, computer simulation, and we create what are called bootstrap confidence intervals. So let's look at an example with a proportion. So suppose I'm just going to create a new proportion here. Suppose there was a political poll, and there was 2,000 people in the poll, and suppose that 1,200 of those people wanted to vote for candidate A, all right, or candidate B, whatever. Let's say candidate A. So we took that poll and we ended up with that result. I think I have this backwards here. Should say 1,200 under count and 2,000 for their sample size. All right, so make sure you don't make a mistake when you're playing around with it. Sample size is the second number, and the count is the number of people who answered the question in a certain way. In this case, yes, I will vote for candidate A. Notice that if you take 1,200 and divide it by 2,000 in the original sample, your sample proportion is 0.6. All right, so 60% or 0.6 is the proportion of people in the original sample who said they would vote for candidate A. All right, so that's the original sample. Now, if you wanted to create what's called a bootstrap sample, all right, which is what we're going to do here. So let's just generate one of these bootstrap samples by hitting generate one sample. What the computer does is does what's called simulation. It randomly picks a number, picks a sample. And how does it pick it? It takes the original sample with 1,200. Let's say if a person is, if you could picture this, if a person is voting for candidate A, they're going to have a happy face. And if they're going to be not voting for candidate A, we're going to have a sad face. You know, so the original sample had 1,200 people with happy faces and 800 people with sad faces. So the bootstrap sample, what they're going to do is they're going to sample 2,000 people from that original sample, but they're going to do it in what's called sampling with replacement. Let me repeat that, sampling with replacement, which means once the computer samples somebody from the original sample, they put the person back into the pot, and it's possible that person could get sampled again. All right. Now, obviously, in a real survey, that's not going to happen. But with simulation, with a bootstrap simulation, creating a bootstrap sample, you will get, I would say, a good chance you're going to get some individuals in the sample who will be chosen more than once, which means there'll be other people in the sample that won't be chosen at all. So in using sampling with replacement, this first sample had 1,179 saying yes instead of 1,200, because they picked probably some additional people who, some of the people said no were picked more than once. And then, and so there was fewer people in this sample who said yes than the original sample. And notice it's plotted right over here. 1179 divided by 2,000 is 0.59 or 59%. So that's our sample. This is our bootstrap sample proportion. So if we generated another one, notice the next one has 1,172 bootstrap samples. I mean, 1,172 people who said yes out of that original sample. So again, in this case, more people who said no were picked more than once. And then, we could generate some more of these. Here's the latest one, has 1,215 out of 2,000 who said yes in this bootstrap sample. This is the last one that was picked out of the 10. And then we generate another 100, another 1,000, and we get a distribution of these bootstrap samples. We click the two-tail button right here. We end up getting an estimate of the population of the population proportion. The original sample that we had was 2,000 people. Maybe the population has 10 million people instead of 2,000 people. And we took a random sample of 2,000. We got 1,200 people saying yes. So they like Canada Day. And then we use the simulation process, creating, in this case, 1,112. This is 1,112 bootstrap samples, all of them having a sample size of 2,000, each one of them having a different sample proportion. All right. Now, some of them had the same, but many of them had different counts. All right. And we ended up with all of this, and then we click the two tails. We end up with an estimate, an interval estimate of the population parameter. In this case, 0.95 represents a 95%, let me repeat that, a 95% confidence level. All right. The number of dots, all these dots here, all of them, black and the red ones, total 1,112. The black ones here, how many are there in the middle here? That's 95% of 1,112. You multiply 0.95 times 1,112, and that gives you the number of black dots. Those are the number of bootstrap samples that are inside this interval. If we wanted to know the number of bootstrap samples outside the interval, well, if there's 0.95 inside, that means there's 0.05 outside, half on each side. So 5% or 0.05 times 1,112 gives us the number of bootstrap samples that are outside the interval. Hopefully that makes sense to you. All right. And how do we interpret this interval here? The way we would interpret it, let me just move this right here. We would interpret it by saying we're 95% confident, all right, that the interval 0.580 at the low end to 0.621 on the upper end. This interval here, we're 95% confident that the true population proportion lies in between these two values. That is, out of all the possible samples that we could create, and we would say 95% of them contain the true population proportion, and we're hoping that this particular one, this particular interval that we created, is one of those 95%. That's what we mean by 95% confident. Okay? Any questions about that? All right, and we could do the same thing. Let's just go back to the original stat key. We could do the same thing for finding a confidence interval for a mean. We could take any of these particular, let's say Manhattan apartments here. We'll take that as an example. Here's an original sample that has 20 apartment values. Now, what is the, this must be rent, I guess. Yes, this is rent. Obviously, Manhattan's very expensive. So we have all of these rents here. There's 20 different apartment rents that are in the sample. So this is a sample from Manhattan apartments, could be thousands and thousands of these, and we took a sample of 20 of them. All right. And suppose we wanted to create some bootstrap samples from this. So here is a bootstrap sample that has all these dots here represent the particular values that came from the original sample, but some of them were repeated. All right, because it's sampling with replacement. Notice that now in this particular, yes, there is a value here, 3,500 in the original sample, that does not show up in the bootstrap sample. Notice that? So there is a 3,500 value here that was not chosen in the bootstrap sample, but there were other values. Notice the one at 2275. Notice in the original sample, there were 4 apartments with that value, and there were many more, 1, 2, 3, 6 of them actually in the bootstrap sample for that same rent value. And again, we can create our bootstrap distribution of samples. How many samples in this case? 1,101 samples. That's what I chose. And again, click the 2. So there are 1,101 total dots here. And if I click the 2 tails, I create my confidence interval. And let's say I wanted to change the 95 with 0.90. And I end up with a 90% confidence interval. All right. And the 95% confidence interval the 90% confidence interval goes from 2688.355 to 3694.473. So you always put those numbers as the lower end and upper end of the interval. We're 90% confident that the true population mean is in between these 2 values. How many black dots are there? It's 0.9 times 1,101. How many red dots are there outside the interval? 1,101 times 0.1. It's the sum of these 2 numbers, right? And that gives us the count. Now, let's look at the boxes on the right here. What are these? This is the original sample, shows us the original sample data. This here is the one of the bootstrap samples. It could be any of these here. Notice I just have to move my cursor around, and wherever my cursor hovers over, that's the bootstrap sample. So I'll choose this one. All right. So this particular sample, here's the mean. Now the sample size is going to be the same, obviously. Here's the median. So it also prints out the median. So pay attention. The mean is here. The median of the original sample, the mean of the original sample, the mean of the original sample, the median of the original sample, and the standard deviation. Excuse me, this is the bootstrap sample's median. So each of these samples, the original sample and the bootstrap sample of one of these, the ones I'm pointing at, has a mean, has a median, has a standard deviation. I can ask any of these questions if I gave you those boxes also. All right, and then the last thing I want to show you, the new stuff, which won't be tested today, but I will test you on quiz number 9 as part of quiz 9 at the end of the semester, is what if we had 2 groups, 2 populations, 2 subpopulations that we were comparing their means and comparing their proportions. So we have what's created here are confidence intervals for the difference in means and difference in proportions. In other words, we're subtracting these 2 population means, and we're subtracting the 2 population proportions, and we want to see what is the range of values for that difference between those 2 populations. So let's look at proportions first. Notice here they use the symbol here, p hat 1 minus p hat 2. So p hat 1 represents the sample proportion for population 1, right? So for example, here is it says using text messages by age. All right, so here are 3 groups, 3 populations of people based on age. There's teens, adults, and then there's people, I guess, or excuse me, there's 2 populations, excuse me. There's teens and then there's adults, all right? So teens up to maybe age 18, adults are older than 18, all right? And then the last thing that's calculated here is the difference between these two groups. So whatever you list first in your database is going to be group number 1, and then the second group will be group number 2. So teens would be group 1, adults will be group 2. So for teens, there were 800 teens in this database, sample size 800, and 696 of them use text messages. All right. Now this is older. Obviously, many more people use them now, but let's assume that this was several years ago. All right. So 696 out of 800. If you divide those two numbers, you get 0.87. 87% of teens in that population sample, use text messages. And then we asked how many adults? 2,252 adults. And 1,621 of them said they use text messages. And if you divide those two numbers, you get 0.72. All right, 0.72. So teen minus adult, if we subtract their proportions, which is really the only category that counts here, is their proportions, we see 0.87 minus 0.72 is 0.15. And that is the difference between the proportion of teens who use text messages and the proportion of adults who use text messages. 15% more teens use text messages than adults, according to this sample, these samples. So this would be the sample difference in their proportions. So if we created a bootstrap sample, again, what they do with the bootstrap samples is they take the same sample, they look at each of these teen and adult samples separately, and they do a bootstrap sample from the teen part, and they do a bootstrap sample from the adult part. Notice these two counts are different, but the sample sizes are the same. And they come up with different proportions. So the sample sizes remain the same. The counts change, but using sampling with replacement, they just do it within each of these populations, the sampling with replacement. So they create a bootstrap sample, and the difference in this bootstrap sample is 0.135. So again, if you create your distribution of these bootstrap differences in proportions, remember all these numbers down here represent the difference between the teen group and the adult group in terms of proportions. So how many do we have here? I think 1,111 of these dots, 1,111 bootstrap samples, the difference in the proportions between the two groups. And then we can create a confidence interval around that. Let's create a 99% confidence interval. Remember, you have to put in a dot there for decimal. All right. And so 99% of the dots, that's 0.99 times 1,111, tells you the number of black dots inside here, inside the interval. And 0.01, 1% of 1,111, the number of red dots outside the interval. All right, and the interval goes from 0.112 to 0.189, and we would say we're 99% confident. Now, the way to interpret this is a little different than when we just have one proportion. We would say we're 99% confident that the true proportion of teens who use text messages is between 11.2% and 18.9% higher than the proportion for adults, right? So that's the way we would say it. But again, we would not say a probability, never a probability. We would say we're 99% confident that the true proportion of teens who use text messages is between 11.2% and 18.9% higher than the proportion than for adults who text message. All right. Okay, and that's how you do a difference between proportions. The interpretation is a little different, but it's the same idea. It's just you have to pay attention to two groups in this case instead of one group. And also, we could do the same thing with means. Go back to the original. And we do difference in means. So, for example, let's just take I guess we can use the one that we have here. Actually, let's let me see. Yeah, that's fine. So now, in this particular case, what are we looking at? The number of hours males and females exercise. All right, maybe in a week, I guess, something like that. And so, what do these dots represent? Well, females represent. Let me make sure I have the right thing here. I believe. Let me think here. Yes. So, group one in this particular case will be the males. Now, how do I know that? Because of the difference in their sample means here. The males are down here. These are all the dots, and there are how many males? There are 20 males, and that's our group number one. Our group number one is 20 males. These are 20 dots. So this particular male exercised 30 hours a week, 27 hours a week, 24 hours a week, like that. Then we have 3 males that exercise 2 hours a week. All right. If you average all of all 20 of these males here, it came out to 12.4 hours on average. Males exercise. Females, there are 30. This is group 2, 30 females who exercise. All right. Who exercise in the, who we picked in the sample and who reported how many hours they exercise. Here's a female exercise 34 hours in a week. Very unusual. There's 23, 20, 17, all the way down to no hours. This one, the female said they didn't exercise at all. And then we averaged all 30 of these females, and we came up with an average of 10, I think 10. Is that right? Maybe not. I think 9.4, probably 9.4. And so, yes, 9.4, there we go. And so the difference in their means, so group 1 is males, it's 12.4, group 2 is females, group 1 minus group 2, 12.4 minus 9.4 is 3. So the difference in the original sample is that on average, males exercise 3 more hours a week than females on average, okay? Then we do our bootstrap samples, create a couple of these, and again, we have the same number of females, same number of males, 20 males, same number of females, 30 females, and we do sampling with replacement within each group, and we come up with different answers here, different bootstrap means. The difference between these two means is 2.22, which is shown up right here, between these two numbers here. All right, and then we continue creating our, we have 2,112 samples in this case. And here's a distribution of all those 2,112 samples. Each one of them has a male group and a female group. There are 20 males, 30 females in all those samples, but with different number of them being chosen with sampling with replacement from the original sample. So we get different means for each of these samples, and we subtract their means, the male minus the female. And then we do our two-tail, and suppose now we want, let's say, a 93% confidence interval. Just be a little different here. So 93% up to 2,112 will be inside this interval. 7% will be outside the interval. Again, we just multiply 0.93 times 2,112 to tell us the number of samples inside the interval, and 0.07 times 2,112 gives us the number of bootstrap samples that are outside the interval, and this is our confidence interval. By the way, in this case here, a negative 1.343 indicates that females this sample here, females actually exercise more on average than males. So that's what this means. And 7.143 means that males average 7.143 hours more than females. So we would say this would be a 93% confidence interval for between these two values here. All right, and these would be the difference in their means. All right. So anyway, it is 2:40 now. So your quiz should be available, and you should keep your videos on during the quiz, please. I hope you've been paying attention. If you were not paying attention, you will probably not do as well in the quiz, because I reviewed everything you needed for the quiz. So go ahead and take the quiz now. You'll have a half an hour to complete it. All right. And just and good luck. And you can use, of course, your textbook. You can use the StatKey. You can have a copy of StatKey open, so you can play with it a little bit in case you need to review what I just went over. Make sure you have a calculator near you, or you can use your computer calculator. The calculations are just very simple. The ones that I was referring to in the during my review there. All right, so go ahead and start, and I will, if you have any questions, send me something through chat. All right, please don't speak out, all right? Definitely make people uncomfortable. So I will stop the recording, and you can go ahead and begin the quiz.